Vector spaces. So vector spaces, these are the main objects of linear algebra that we study. What is a vector space? So a vector space, right? This is the term we're defining. A vector space, V, right? V is our name for this vector space, is a set of elements called vectors, right? So vectors are the particular elements in this collection, right? This set that we're calling a vector space. And there are two operations that we're defining. There's an operation written as plus, which we'll call vector addition. There's an operation written as times, which we'll call scalar multiplication. And these operations in this set, they get to be called a vector space if all 10 of the following properties hold. What has to be the case? These operations have to be closed. The addition has to be nice. The multiplication has to be nice. And the addition and multiplication have to play nicely together. You might be wondering why I said there were 10 properties and then I just listed four. Well, because there are subparts. These are the four categories of properties, but we're going to have a 1A, 1B, we're going to have a 2A, 2B, 2C, 2D, right? So there are subparts, and with all the subparts, it's going to add up to 10. Before you close the video, and he's going to teach you how linear algebra. You can't even count to 10 properly. Let me find a different video on vector spaces. So this is our mission, is to list out these properties. You may have seen vectors before in the sense of an arrow with direction and magnitude, say in a physics class. That's the most common way that it's discussed. You may have also seen it, say, in a computer science context, right, where it's or say like a multivariable calculus context, right, where it's a list of numbers, right, where it could be some number and some number, right, and often these two approaches are compatible, of course, right. You can think of maybe those numbers as being components, maybe a horizontal component and a vertical component of a vector that is representing, say, a force in physics, right? So these are totally compatible perspectives. What we're doing here is we're generalizing this notion of a vector, right? And what we're doing with these 10 properties is we're saying, what are the key behaviors? What are the key properties, the key identities that govern vectors, whether you're thinking of it as force vectors or if you're thinking of it as a list of numbers? In either of those interpretations, what are the key algebraic properties that are satisfied by such objects? And then anything that behaves algebraically like vectors in the force vector or in the computer science vector interpretation, right? Anything that behaves like those, we will call that a vector space, even if it's not force vector, right? Even if it's something different. So that's what we want to do. I want to list out these properties, and side by side with these properties, I want to show an example, because I think, typically in mathematics, you state a definition and then you show an example of that definition. Here, the definition is so long that if you wait until the end of the definition to show the example, that's the first part of the definition is ancient history by the time you've shown your example. So here I'll show the most common vector space, at least in sort of K through 12 and beginning undergraduate mathematics. The most common vector space by far is the plane, the good old XY plane, right? So let B equal the Cartesian coordinate plane, right? Another way to look at this is, we typically call it's just lists of numbers with two real numbers in it, right? The first one we call X, the second one we call Y, where X and Y are both real numbers. This is, right, so it's the set of all numbers, the set of all pairs of numbers, ordered pairs of numbers, X comma Y, right? And so that's our set. And then addition is defined component-wise, right? What does component-wise mean? It means that if you add two vectors together in this vector space, you just add the components, right? You add the X components, you add the Y components, and that gives you another vector. And also that scalar multiplication is also done component-wise. What does that mean? This means that for any real scalar, you could take a real number times a vector by just multiplying each component by that real number. Right? This is our definition of vector addition in this case and of scalar multiplication. One thing to note here is here I'm implicitly saying that our scalars come from the real numbers. You can do vector spaces where your scalars are the complex numbers. You can do vector spaces where your scalars come from a finite field, where there are other ways to do it. For an introduction to linear algebra, typically you work over the real numbers as your scalars, but just be aware you can do this with other sets as your set of scalars, as long as certain algebraic properties are satisfied. So let's then look at these properties. So this is here, all I've done is I've defined what is V, right? So V contains what kind of things are in V. There's anything that's a pair of real numbers, right? So 0, 0, 1, 3, 2, -1, right? E, comma, 1 minus pi, right? These are all elements of V, right? It just looks like pairs of real numbers. And we typically represent these visually, right? How do you represent these visually? You just draw an x-axis and a y-axis, and 0, 0, you draw like that. 1, comma 3, we draw like that, and so on, right? So this is our typical visual representation of this set V, which is r squared, right? So, all right, so let's, I'm claiming this is the canonical example of a vector space. So let's look now at these 4 categories of properties that I claim will total to 10 properties. So I said that the operations are closed, right? What does this mean? This means, so we're going to have the 2 operations, right? Plus and times. So for plus to be closed, for V to be closed under plus, right, under this operation of vector addition, what do I mean by that? So to be closed under addition means that if I pick 2 vectors from my vector space V, right? So if V1 and V2 are both elements of V, then when I add them together, I again get an element of V, right? So that's why they call it closed, because it's like the set V is, if you think of like a Venn diagram, right? V is this this circle that you pick 2 elements inside that circle, you add them together, and that border is sort of closed. They can't leave that circle, right? There's some. So here, this is certainly true for this case, right? For every vectors, if I pick 2 vectors in V, right? By nature of what this V is, I get that you can write each of these as some ordered pair, because it's the vector space we're dealing with is ordered pairs of real numbers, right? So for these 4 real numbers, for these 2 vectors, there will exist 4 real numbers that represent their coordinates. So then I can do this component-wise addition. And when I do this component-wise addition, I get x1 plus x2, y1 plus y2, and that, by definition, is again an element of V, because that's another point in the plane, right? We're saying that if we take, right, one vector v1, and I add to it another vector v2, right, then their sum, v1 plus v2, is still in this set, right? V represents the entire plane. So this is closed under vector addition, right? Adding 2 vectors in the plane produces another vector in that same plane, right? What would it mean to not be closed? Say cross product, right? If you take 2 vectors in the xy plane and you take their cross product, you don't get another vector in the xy plane. You get a vector that has a z component, right? So say cross product. It would not be this set V would not be closed under cross product. It is closed under addition, right? So that's what we're seeing here. Okay, so there's closure of addition. Now, the second operation, the second property here is to be closed under the other operation, scalar multiplication, right? So to be closed under scalar multiplication, what does that mean? It means that for every real number r, and again, you can do this over the complex numbers, you can do this over finite fields, but it's for a first pass at linear algebra, typically you just work with the real numbers, or at least mostly with the real numbers. So you pick a real number and a vector in V, or scalar multiplied by V is again an element of the vector space V, right? So this is 1B, and it's also closed under scalar multiplication, and this works as well, right? If you have, I'm going to shortcut the variable declaration a little bit here. So you have vector V, which then is equal to some x comma y, right? And you have some real number r. We're going to have rv equals rx ry. Well, that's again a pair of real numbers, therefore it's still in V, right? And again, you can think of a little visual representation of this, right? If you have some vector V, oh no, don't go away. There we go. If you have some vector V, the x-axis is underpaid apparently, and then you multiply it by some scalar r, right? You get another vector in the same plane, right? It's kind of like in contrast to, say, the example I gave before, cross product, right? If you take a real number and multiply it by v, that vector in the xy plane is not now going to magically grow a z component like it does with cross product, right? Here, it just stays in the xy plane when you multiply it by a real number r. So therefore, this vector space is closed under addition, right? This checks out, and it's closed under scalar multiplication, right? So those are the first two properties of being a vector space. It passes both of those. So let's now look at 2. 2 says that addition must be nice. All right, what does it mean for addition to be nice? It means there needs to be an additive identity. So what is an additive identity? It means that there exists a special vector called the additive identity. And typically, it's written 0 with a vector hat on it. Doesn't mean it has to literally be what you might call the zero vector, and again, say in physics. But we write it that way. Right? Sometimes we'll put a subscript v to denote what vector space is the zero vector for, or sometimes you'll just put zero vector if the context is clear what vector space it lives in. But there exists this zero vector such that what defines the zero vector? Well, it needs to be that no matter what you add it to, right, for all vectors v, you need that if you add the zero vector to v on the left or on the right, you just get back v, right? You just get back that original vector, right? So it's the operation that preserves the identity of any, sorry, it's the vector that preserves the identity of any other vector when you add it. So this is property, right? This is property 2a. And here, the zero vector, the zero vector is literally 0, 0, right? 0, comma 0. And, if you think about it for any other vector, x, y, if you add 0, 0 to it and you're doing component-wise addition, you just get x plus 0, y plus 0, which is x, y. You get x, y back, right? And it works the other way as well, right? So this is additive identity. It passes that property just fine, right? 2b is commutativity. Oh, sorry. Let's do additive inverse. We'll do additive inverse next. Then we'll do commutativity. So additive inverse, this one is almost like a special case of scalar, but that's maybe not obvious up front. But this it's almost like scalar closure but for -1. So here is what additive inverse is. For every vector in your vector space, there exists a vector that you can add to it, which you could just call W sub v or something like that. But typically the symbol you give to that vector, the additive inverse, is -v, right? So -v is how you call the additive inverse. This, right, is a vector that has what property? You want this vector to have the property that if you add this vector to v, again, either on the left or the right, it brings you back to the 0 vector, right? This is the additive inverse. And this vector space, the plane, definitely satisfies additive inverse because any vector xy has additive inverse what? Well, -x, -y, right? That's the vector that you could add to xy to get back to the 0 vector, right? Since xy plus -x, -y equals x minus x, y minus y is 0, 0, right? That gives you the 0 vector when you add it. And it works on the adding to the left or adding to the right. So, all right. The next is commutativity of addition, right? The commutative one. And what there's no and in this. For some reason, common mispronunciation I hear. That's ironic. What I just mispronounced is it's not commutative, right? It's commutative. And the reason it's commutative is it means they can move past each other, right? Like drivers on the highway. So for all v and w in v, right? If you add v plus w or you add w plus v, you get the same thing because w and v, right? They can move past each other. So this is the commutative property of addition, right? Here, and again, I'm not being super formal about my variable declarations here or anything. I wouldn't call what I'm writing a formal proof or anything like that, but I'm sort of just doing some key calculations that verify that these properties hold, right? So here, if you add two vectors to each other, well, if you're adding component-wise, we know the basic arithmetic of real numbers is commutative, right? So you could swap the x1 plus x2 for x2 plus x1 and y1 plus y2. You could swap for y2 plus y1. And then by definition of vector addition, well, that's the same as adding those in the other direction, right? So this, oh, I missed the check mark for inverse. So this set does satisfy commutativity of vector addition, right? All right, there's the commutative property of addition. There's one more, which is the associative property of vector addition. And that says if you have three vectors, right, v, w, let's say v, let's say u, v, w, right, all in v. So pick your favorite three vectors. Then what has to be the case? Well, we have to have that u plus v plus w, right? If you add the three vectors by first adding up v and w and then tacking a u on, that has to be the same as if you first add up the u and the v and then tack the w on after the fact, right? So it's almost like a commutative law for plus signs, right? We have two plus signs and it's saying it doesn't matter which one you do first, right? You can do the second plus sign first, which is what I have written on the left there, or you can do the first plus sign first, which is what I have written on the right. And it doesn't matter which one you do, right? So because of that, when it's when it is commutative, then we tend to write things just like this. You just put u plus v plus w. You don't need to put any parentheses on that expression because it's the same either way. So it's well defined to write something like u plus v plus w without any parentheses. So associative really cleans up your notation, right? Here, this is proven very similarly to the commutative property, right? If you kind of just piggyback it off the fact that the addition of real numbers is commutative, right? So if you add, here you add these vectors, you add up three vectors, and first I evaluate the second plus sign, right? So then I add the first plus sign, and I'm adding component-wise, right? But then I can apply the associative law in there, right? Inside the components. Right? And then take it back apart and say, ooh, okay. Now I've changed which vector addition happens first because I was able to take it back apart in a different order than how I put it together. There we go. Right, so now I have these vector additions being done in the opposite order, right? So there's the associative law, right? So it's it does satisfy associativity of addition. All right. What happens next? We have multiplication needs to be nice, right? All right. I think I need to write bigger on the property side because the example side is outpacing the property side. So what do I mean that multiplication is nice? Well, 3a, we need an identity of multiplication, right? So multiplicative identity. What this is this says that for every vector v in your vector space, 1 times v equals v, right? So here 1, now this is really something different from when we said zero vector, which 0 just represents really any element of v that satisfies a certain property. Here, when I say 1, I mean the real number 1, because I'm working in a real vector space where my scalars are real. So when I'm doing scalar multiplication, I'm multiplying by a real number. So I'm saying the real number 1, when you multiply, needs to leave that vector unchanged. Right. So this is multiplicative identity. While we're over here, let's also say associativity of multiplication. I put it in quotes because for a little technicality, it's not quite perfectly an associative law. So you want for all R and S, all real numbers R and S, and for all vectors V, we want R times SV to be RSV. It's nice to think of it like an associative law because it's sort of shifting parentheses, just like we had for addition, right? What's different here is that on the left, we have a scalar multiplication of a scalar by a vector, and then we have another scalar multiplication of a scalar by a vector. On the right, we have ordinary multiplication of two real numbers, and then a scalar multiplication of a scalar by a vector, right? So technically there's two different properties happening, two different operations, right, on the left versus on the right. So that's why I put associative in quotes there, right? It's not quite a proper associative law, but it's nice to think of it that way. Because it has that appearance, right? Shifting parentheses. So now in this case, 3a, yes, if you do component-wise multiplication with the number 1, you just get 1x, 1y, great, that's just xy, right? So sure enough, we have that 1v equals v for all v, right? Part B, here if you have R and then SV, right, you multiply the S into your vector, then you multiply the R into your vector, component-wise. And then in here, this now is an ordinary associative law because this is just three real numbers multiplied together. So I apply just an ordinary associative property, right? But I do it twice. Right? And what does that become? That becomes RS X, Y, right? So that is this pseudo-associativity of scalar multiplication. Okay, great. So there's 3A, 3B. Now, that was what it meant for multiplication to be nice, right? The identity and the pseudo-associativity law. Then we have that addition and multiplication must play nicely together. What is that called? More formally, that's called the distributive law, right? So, right, distributive law describes how addition and multiplication interact. Here, though, we have two different distributive laws, right? So the first distributive law says what? It says that if you have a scalar added to another scalar times a vector, that's the same as adding together the sum of each scalar applied to that vector, right? So this is saying that vectors distribute over addition of scalars, right? That's one way you can do a scalar, a distributive law. But there's another way, right? You could, it's a different property entirely, right? You could say, or the, I want that, so distributive law 2, right? I want that a scalar distributes over a sum of vectors. That's another way that you could write down a distributive law, right? And here, and also this is for all. I should specify this is for all vectors v and for all scalars r and s, right? This has to be true. This has to be an identity for all real numbers and all vectors in your vector space. And same thing here, right? For all, this is for all vectors v and w and all real numbers r, right? This has to be the case. So these are the two distributive laws. And here, again, you can check these, right, by just calculating. So you could say, I pick arbitrary real numbers r and s, I pick an arbitrary vector v in v, which in this case is the plane. I say this is r plus sx, r plus sy. I distribute that, I get rx plus sx, I get ry plus sy. And then I can now break this apart into rx, ry plus sx, sy, which becomes rxy plus sxy. And there we go. I just verified that vector will distribute across addition of scalars, right? And I have one last thing to check. For B, very similar, right? I want R to be added to 2. Sorry, R to be multiplied by a sum of 2 vectors. And so what happens here? Well, working inside the parentheses, following order of operations, right? First I add my vectors, and then I multiply it by R. Component-wise, right? Then I apply the ordinary distributive law for real numbers. And after I do that, right, I can take that back apart as a sum of vectors. right? And when I do that, I have proven that R times the sum of vectors equals R times the first vector plus R times the second vector, which is the other distributed law, right? So what is the conclusion of all of this? Well, since V, which in this case was the plane, right, with component-wise, right, with component-wise addition and scalar multiplication, right? Those are the operations. Since that satisfies all 10 properties, right? It has to satisfy all 10, right? If it fails even one property, we would say not a vector space, right? But since it satisfies all 10 properties, right, we say this is a vector space, right? This gets to be called a vector space, right? And there are lots of other vector spaces out there. We will see other examples of vector spaces, but this is I think the most familiar example of a vector space, right? We'll see plenty more examples of sets and operations that satisfy all 10 of these properties. But this is maybe the most famous, most important, right? One quick generalization of this. If you do component-wise addition and component-wise scalar multiplication, Rn is a vector space for any natural number n, right? So just like the plane xy plane is a vector space for n equals 2, if you did xyz, right, and n is 3, so now you have triples of real numbers, essentially exactly the same argument that we wrote out here. It all still works. It's just now everything has a x1, y1, z1, or x2, y2, z2, right? So it's just tack a third component onto all of your vectors, and the same proof works, right? So this is um, probably the most famous family of vector spaces, right? The is in tuples of real numbers, right? So, all right, great, thank you. So there's the definition of vector space, right? This giant long left-hand column, these 10 properties, that's the definition of vector space. On the right, we have our most famous example, R2, which then generalizes to Rn, right, to n-dimensional real space. Great, thank you. More adventures with vector spaces very soon.